Hey everyone, I'm Crisaldi Tugade, and today we will discuss flash distillation. Okay, so let's get started. Flash distillation can be considered one of the simplest separation processes or operation. In this process, a pressurized feed stream which is in liquid phase is passed through a throttling valve or an expansion valve. Sometimes the feed stream may be passed through a heater before being passed through a valve or nozzle in order to preheat the feed, but it is connected to a tank or drum which is called a flash tank or drum. Again, most designers are having difficulty in designing flash distillation, most especially students in plant design and ED, because sometimes they assume that the feed stream in a flash distillation consists of vapor and liquid. But that's not the case. For a flash distillation to occur, or for the design to be effective, it must be in liquid phase and pressurized. Okay? In order to separate a flash distillation, in order to separate these two phases in the flash drum, a throttle or expansion valve will only be used. It is used to suddenly change the pressure of the feed. Okay? So, we have here a diagram. Let's consider that as figure 2.1. It's a flash distillation system. Okay, so we have your feed here. It is being pumped through a heater, which is going to the distillation, or this is what we call a flash drum. But before it proceed with the flash drum, before the separation occurs, you have here a valve. This is a throttling valve or an expansion valve. Okay, so for the feed streams, let's consider Zi or Zi as the composition of species I, T1, temperature 1, pressure 1, and enthalpy 1. Okay, for the feed, of course, the composition of the feed before the pump and after the heater will just be the same. Okay, so it's just the same as that of Zi, TF, but of course the temperature and the pressure as well as that of the enthalpy will change because there is a heater used. Okay, and then after that, in the distillation system, it will be separated into vapor phase and liquid phase. In the vapor phase, we make use of Yi. It's the mole composition of the species in the vapor phase, the temperature of the drum, the pressure of the drum, and the enthalpy of the vapor. In the liquid phase, we have here Xi. Again, it represents the composition of the species I in the liquid phase, the temperature of the drum, the pressure of the drum, and the enthalpy of the liquid phase. Okay, so let's proceed now with the overall material balance or the mole balance of the system. It is in the dashed boundary. This is the dashed boundary, which can be written, as we all know, that would be the mass or the mole of the feed will just be equal to the mass or the mole of the liquid phase plus the vapor phase. Okay, for the species I, again, we say that Zi or the Zi represents the composition of the species I in the feed, Yi represents the composition of the species I in the vapor, and Xi represents the composition of the species I in the liquid phase. So that would be ZIF will just be equal to XIL plus YIV. That would be for the material balance in the distillation system. Okay, now we proceed with the energy balance for the system. So for the energy balance for the system, we will have the feed multiplied by the this one, we're only talking here of the flash distillation system. Feed multiplied by the HF or the enthalpy of the feed plus the Q of the flash drum or the heat of the flash drum is equal to the liquid phase multiplied by the enthalpy of the liquid phase plus vapor multiplied by the enthalpy of the vapor phase. But we need to consider that most often flash distillation is operated adiabatically, it means that Q flash will just be equal to 0. Therefore, equation 2.3 can be reduced to FHF is equal to LHL plus VHV. So that would be the energy balance only for the flash distillation system. Now, what if we will consider now the heater used? Okay, to determine the amount of QH, or to determine the size of the heater that we need to use, of course, in the design, it is very important. Energy balance around the heater is performed as follows. So if this is what we want to know, the QH, so that would just be equal to the feed multiplied by the enthalpy 1 plus the supplied heat in the heater will just be equal to the feed multiplied by HF. It should be noted, if the feed only contains two components, it results in the following facts. Before being fed into the tank, this is the tank, before it being fed into the tank, it only compose or contain one phase, which is a pressurized liquid stream. After being fed, it will be separated into two phases, which is the vapor phase and the liquid phase. You need to remember that, okay? It's very important, most especially in the design. So for the flash distillation, we now talk of the equilibrium data. So we have had a previous discussion regarding vapor liquid equilibrium or phase equilibrium in general. So I've let you watch a video tutorial. I just hope that you remember it now because it will come handy. Okay, so in principle, chemical equilibrium data of liquid and vapor can be obtained experimentally. If we now consider here a chamber containing liquid and vapor of a mixture, let's say that we have here a vapor phase at top, and the bottom or the grayish part is the liquid phase. At specified temperature and pressure where both phases are allowed to be settled, meaning that the vapor phase and the liquid phase have already reached equilibrium, we will be able to have this set up. Okay, in figure 2.2. Now, you need to remember again, when can we say that the system already reached equilibrium? You need to remember that when the Gibbs energy of the vapor phase is equal to the Gibbs energy of the liquid phase, that is the time that we can say that the system already reached equilibrium. And in that sense, again, babalikan ninyo yung mga natakal ninyo in Fichem 2 or in Thermo 2 about Clapeyron equation and Clausius-Clapeyron equation. It is very important, okay? Most especially again in the design. Kasi this phase equilibria will determine, or if not, it will help you solve for the boiling point elevation, freezing point depression, osmotic pressure, and the like. Okay, so you just need to remember of these things. We proceed. Normally, the experiment can be conducted in either constant pressure, where the system's temperature is varied, or constant pressure, where the pressure of the system is varied mode. Okay, you need to note that if we are talking of a binary mixture, we know that the summation of all the XA in this part, if a binary, that would be XA plus XB will just be equal to 1, and YA plus YB will just be equal to 1. Because we are talking here of a binary mixture, means that we are only talking of two components present. Okay, in the table 2, it illustrates the equilibrium data for various temperatures of the system containing ethanol E and water W at the pressure of 101.3 kilopascal or 1 atmosphere. Okay, this table 2.1 can be also presented graphically as a YX diagram. This is what we call a McCabe-Thiele diagram. We will be able to see this in the next figure. A TXY diagram, temperature composition diagram, or if temperature is held constant, it can be a PXY diagram, and an enthalpy composition diagram. This enthalpy composition diagram is most often used in solving for the number of theoretical stages using the Ponchon-Savarit method. So we will have a separate discussion on that. We'll just focus on the YX diagram for the time being and TXY or PXY diagram. So table 2.1, here you will be able to see the VLE data for the ethanol water binary mixture at 1 atmosphere. You have your XE represents the mole fraction of ethanol. XW represents the mole fraction of water. X again, here you need to remind yourself that X represents the composition in the liquid phase. Y represents the composition in the vapor phase. So for the flash distillation, that would be figure 2.3. That is a YX diagram for ethanol water. And then figure 2.4 illustrates a TXY diagram for ethanol water binary system. So, actually, I will tell you that this one looks familiar already with you. Okay? So, for figure 2.3, kung mapapansin ninyo, wala lang dito yung X is equal to Y line. Okay, so yung line na nakikita natin pag mag-KCL is yung isang diretsong line na nagre-represents ng ganon. So I suppose kapag na-plot nyo yun, this one will looks familiar with you. Now for the TXY diagram, kung mapapansin niyo, etong mga triangle na to and circle that you will be able to see in the graph, it was made isothermally. It means that at the same temperature, this is the composition of this species at this liquid phase and at that vapor phase. Okay, note that in figure 2.4, a solid line, Tx, is a saturated liquid. So, ito yung sinasabi niyang Tx. This line is a saturated liquid. Okay, Ty is a saturated vapor line. This is a saturated vapor line. Okay, and for ethanol water binary mixture, you will be able to know that there is an azeotrope. The azeotrope is at 0.8943. Y ethanol and X ethanol is just equal to that. It means that again, you have already tackled vapor liquid equilibrium. I presume that you already know what an azeotrope is and how do we break this azeotrope point to further increase the distillate composition. Okay, so we proceed. Let's consider the flash distillation system again. Let's see the figure 2.1. The material balance is just a repetition. So that would just be equal to F is equal to L plus V. And the species balance is just equal to ZI. F is equal to XI L plus YIV. So if we will try to rearrange that to isolate YI, we will have Yi is equal to negative L over V Xi plus F over V Zi. So, anong ginawa natin dito? We take the y-intercept form, okay, of the material balance equation. So, again, Yi represents the species at the vapor phase composition. Xi, again, represents the composition of the ice species in the liquid phase, and Zi represents again the composition of the ice species in the feed. Okay, so in this case, in this formula, if you will see that the slope is given as negative L over V and the y-intercept is given as F over V. Okay, so you need to remember this, that F over V is equivalent to L. It can be expressed as such. It means that F is the fraction of the feed that vaporizes. Okay, this F. And L over F is equivalent to Q, which is the fraction of the feed that remains liquid. Okay, it's the fraction. Okay, we proceed. Now, let's go back now to the equation 2.6. We say that this is the equation for 2.6. Now, what is F over V? Let's go back again. F over V is equivalent to F. Let's try now to express the whole of this into F. Okay, so if F over V is 1 over F, 2.6, equation 2.6 will yield Yi is equal to negative 1 minus F over F multiplied by Xi plus Zi over F. That will give you now equation 2.8. And this equation 2.6 can also take the form y is equal to negative q over 1 minus qxi plus the quantity 1 over 1 minus qzi. Again, it is just the same. 2.6, 2.8, and 2.1 are just the same. It is just expressed differently. Okay. How? Because of F, Q, and the material balance only. Okay. So no, see here, see the note here. Note that equation 2.6, 2.8, 2.11 are in fact equivalent to one another, and they are the operating equations for the flash tank. Okay, in which, if you will see, given 2.6, the slope for 2.6 is negative L over V. This is negative L over V. For equation 2.8, that's negative quantity 1 minus F over F. And for equation 2.11, that would be negative Q over 1 minus Q. Negative Q over 1 minus Q respectively. And for the y-intercept for 2.6, that is F over V, Zi. For 2.8, that is Zi over F. And for 2.11, we have here 1 over the quantity 1 over 1 minus Q multiplied by Zi respectively. These are just the same. It was just expressed differently. Okay. Now, to solve this, to solve the amount, the composition at equilibrium in a flash distillation, we make use of a graphical solution. It's much better again to make use of graphical solution because it will yield you better broad or scope of the assumptions. So mas konti ang assumptions na ginagamit pagdating sa equilibrium, unlike for a graphical solution. Unlike for analytical solution, marami ng assumptions made to simplify it. Okay, so to solve the equilibrium composition, we need to graph here the operating line. Ito yung kanina nating sinosolve. Equilibrium data, ito yung mga experimental, and the y-x line. Okay, so if you will see this, the intersection of the equilibrium curve, this is the equilibrium curve, and the operating line, this is the operating line, let's say for the time being, the intersection of the operating line and the equilibrium line will yield or will give you now the equilibrium composition. So at this point, we're in this equilibrium data and operating line intersects, that will give you the equilibrium composition. Okay, so let's try to solve this sample problem using graphical solution. So consider an ethanol water system wherein V over F is equal to 2 over 3 and the feed composition of ethanol is equal to 0.4. Solve for the composition of ethanol in L and V. Locate the feed point. Okay, so what do we need to remember? What is F over V? So given, we have F over V is equal to 2 over 3. But remember that V over F is equal to F, which is equal to 2 over 3. And the slope for the operating lines are CF. We need to confer equations 2.6, 2.8, and 2.11. Sorry. So since F is already given, it is better if we use equation 2.8. Now to solve for the slope of equation 2.8, the formula is negative quantity 1 minus F over F. Okay? That is to solve for the slope of the operating line. And that will give us 1 negative 1 minus F over F is just equal to, again, F is equal to V over F, which is equal to 2 over 3. So that would, let's just try to substitute here. F1 minus the F 2 over 3 over 2 over 3. That will give you now the slope of negative 1/2. That is the slope of your operating line. Now to solve the y-intercept for the operating line, again, anong kailangan nating hanapin doon? Of course, yung may F na. And that will give you now equations 2.8. So for the y-intercept of equation 2.8, that is Zi over F. So for Zi, ano ba yung sinabing? Given sa atin is yung ethanol. Let's go back. Diba? I here is the ethanol, which is 0.4 over the F is 2.3. So 2.3, 0.4 over, that's not 2.3 but 2 over 3, 0.4 over 2 over 2 divided by 3 will give you 0.6, and that will be your y-intercept. Now, that is equation 2.8 here. This is equation 2.8. Therefore, the equation of the operating line is y eto is equal to negative 1 half x eto plus 0.6. If you will plot this now, that this one is your equilibrium curve. That is your equilibrium curve. This is your operating line. See, the y-intercept is 0.6. The slope here is negative 1 half. So this is now your operating line. That is your equilibrium curve. And this is your y is equal to x line. Okay. Again, the intersection of the operating line and the equilibrium curve will give you the equilibrium concentration. In that case, the equilibrium concentration for ethanol in the liquid phase is 0.17 and in the vapor phase that is 0.53. Okay? So, napakasimple lang ng pagkuha ng equilibrium concentration using graphical solution. Now, what if we are asked to solve for analytical solution? Okay? So, pag nag-analytical solution tayo, there's another property that we need to consider, and that would be relative volatility. Why do we need to enter this into record? Because kailangan natin. Okay? So, relative volatility of AB is just equal to YA over XA all over YB over XB. Again, this is only for binary solution. Further, it can be expressed in terms of relative volatility AB is equal to YA over XA all over the quantity 1 minus YA over the quantity 1 minus XAY, because again, the summation of all the X or XA plus XB is equal to 1 and YA plus YB is equal to 1. That is for the binary solution. And then it will give us equation 2.17b, which is equal to relative volatility is equal to YA times the quantity 1 minus XA over XA multiplied by the quantity 1 minus YA. Okay, this is only for ideal solution. This is the assumption if the gas phase forms ideally an ideal gas mixture, and for the liquid phase it forms an ideal liquid solution. We have already tackled this in the vapor liquid equilibrium. When can we say that we form an ideal gas, and when can we say that we can form an ideal solution, ideal liquid solution? So given that note, I know that you should have known this already. Okay, so we have had several exercises and some reading materials. You should have known the parameters. When can you say or when can you assume ideality of gas and ideality of solution? Okay, so when we try to rearrange this, we have the equilibrium curve equation. Okay, so yi, let's go back again. Okay, so yi will just be equal to xi multiplied by the relative volatility over the quantity 1 plus the quantity alpha minus I multiplied by xi. Please note again that alpha, aside from being expressed in terms of the mole composition, it can also be expressed in terms of its saturated vapor pressure and the total pressure given in equation 2.20. To obtain the analytical solution for the flash distillation, equate 2.1 with one of the operating line equation. So yi is equal to quantity 1 minus f over f multiplied by xi plus zi over f. Remember that this is equation 2.8. This is the one that we use in solving the prior solved problem. Okay, now if we now try to substitute this equation, this 2.21 equation in this equation, this will give us this equation. Okay, that is equation 2.23. There's no point in deriving this equation, you just need to remember this. Okay, so But you can, if you try to substitute this 2.21 here, it will yield you the same answer, the same equation as that of equation 2.23. Okay? So this is for the graphical analytical solution of flash distillation to know or to determine the vapor phase composition and the liquid phase composition. Okay, so for your exercise, I want you to solve the composition of L and V given the same problem. Okay, by the way, let's go back here to the here in the graphical solution. Now, if you will see, you're supposed to have the same answer as that given, not the same but close enough answer as that of our graphical solution. Okay, so what if we are now dealing with a flash distillation of multi-component? It's no longer binary. Yung kanina, puro binary mixture lang yun. We say that XA plus XB is equal to 1, YA plus YB is equal to 1. Now, I know that you already know this. Okay, for the flash distillation, multi-component, in thermodynamics too, we make use of the de Priester chart. Okay, so let's just try to recall that YA, that YI is just equal to KIXI. Again, this K, we can use the K chart by de Priester to look for this, to look for the value given a temperature and pressure. Okay, for light hydrocarbons, the value of Ki of each species can be obtained from the graph, which is available in McCabe-Thiel, in Van Ness, and in our handbook. In our handbook, we make use of figure 13-9 to know the values of this K, or to look for the K charts. Okay, so for example, figure 2.6 is the K chart for the low temperature range. 2.7 is K chart for high temperature range. So in this side, on the right side here, you will have the temperature in terms of degrees Fahrenheit. On this side, on the left side, you have here the pressure. In between here is the species here. And the numerical value in between of these will give you now the value of your K. Again, in order for you to know K, you need to know temperature and pressure. So the meaning of Ki on the K chart can be described mathematically by the original Reynolds law and the modified Reynolds law as follows. So Yi over Xi is equal to saturated vapor pressure I over P. It yields Ki is equal to the saturated vapor pressure of I species over the total pressure. So species balance for the multi-component distillation, it's just the same. ZIF is equal to XIL plus YIV. Now, if we try to substitute again, what is K? K, if Pi asterisk or the saturated vapor of the species I over P is equal to Ki, and Ki therefore can be expressed as Yi over Xi, therefore Yi is equal to KIXI. So that would be KIXI. We'd now try to substitute it there. Okay, so if we now okay, so if we now try to divide and multiply this by L over L, this equation, that will give us ZIF is equal to XIL multiplied by 1 plus KIV over L. Okay, so if we try further to arrange this, I want to isolate XIL. So if we isolate XIL, that will give us ZIF over the quantity 1 plus KIV over L. And that will give us equation 2.48. So by algebraic but you need to remember that the summation of Xi multiplied by L will just be equal to L multiplied by X, the summation of Xi. Okay, and further it can give you here. What I'm trying to say to you is that the summation of this, of ZIF over the quantity 1 plus KIV over L will give you now the total or the total amount of L. It means that the total composition or the flow rate of the liquid phase. So solving for Yi, we have equation 2.50. as you may read there. Since it is equilibrium, even though for a multi-component, it doesn't matter that the mole fraction in the liquid phase must be equal to 1 and the mole fraction of the vapor phase must be equal to 1. You just need to remember these equations, 2.51 and 2.49. Okay, now, you know that for a multi-component flash distillation, to solve for the equilibrium concentration, it is a trial and error. Okay, to solve for the value of L, the trial and error technique must be employed such that the value of L is guessed and the corresponding value of V is obtained from the fact that V is equal to F minus L. Okay, so paano ba natin gagawin yon? Let's see in the example later para hindi na rin tayo maguluhan. But when we solve for this multi-component flash distillation concentration, ang kailangan natin dito is we first set the value of L and then we compute for the value of L using equations 2.51 or 2.49. So if the assumed L is equal to the computed L, that's the time that we can proceed further with our calculation. Okay, so let's see for the sample problem. For the sample problem, a flash chamber operating at 50 degrees Celsius and 200 kilopascal is separating 1000 kilomole per hour of feed containing 30% bimole propane, 10% N-butane, and 15% N-pentane, and 45% N-hexane. Find the product compositions and flow rate. So we have in here the process flow diagram, a block diagram for this. So we have here the temperature of the drum to be 50 degrees Celsius or 122 degrees Fahrenheit. The pressure of the drum is 200 kilopascal or 29 psia. Okay, so note for the time being that Z1, that 1, 2, 3, 4 that you will be able to see here is pertaining to 1 propane, 2 N-butane, 3 N-pentane, and 4 N-hexane. Okay, so we are asked to solve for V, YI, L, XI. Okay, so anong sabi ko kanina? Kailangan muna natin makuha yung values ng K natin for this. So we make use of the Depriester chart or the K chart. Okay, so you locate here 122 degrees Fahrenheit in the right side. So let's say that is 122. 200 kilopascal or 29 psi on the left side. So you need to connect a point to form the line. Okay, and upon forming the line, you look now for the species you want to get K. Okay, for K1 that is propane. So propane is here. You look for it. It intersects here. Therefore, the value of propane is around 7. For N-butane, N-butane is here. So you look for that. That is your point. That is 2.4. Followed by N-pentane. N-pentane. Oh, this one. Very small. So N-pentane, that would be your point. And then you get K, 0.8. And lastly, for N-hexane, that is your point. That would be 0.30. So the first thing you need to solve is to look for K. Okay, followed by your assumptions. Now we go to the trial and error part. Okay, so again, anong sinabi natin kanina? We first assume the value of L and then we calculate for that value of L. If L assumed and L computed is the same, we can now proceed with further calculation. But hanggang hindi yun nag-i-equal, you need to look or you need to solve wherein the L assumption is equal to L computed. Okay, for the first assumption, we say that L is equal to 100 moles. Okay, so if L is 100 moles and F is 1000 moles, we can say that V is equal to 900 moles. Okay, so the value of L can be computed using equation 2.49 as illustrated here. This is 2.49 as illustrated in the following table. Again, Zi represents the composition of species in the feed. So for the propane, that is 0.30, and butane 0.10, N-pentane 0.15, and N-hexane 0.45. This is all given. Ki, this is what we tried to look for a while ago using the K chart. So for propane, we have 7, N-butane 2.4, N-pentane 0.8, and N-hexane 0.30. Now, Li, in this case, Li, this is the formula. Sinabi natin that the summation of this will give you L. Ayun yung sinasabi natin dito. Now, Li represents the species, the flow rate of the species in the liquid phase. Tandaan natin ha, Li is the flow rate of species in the liquid phase, and that will be equal to ZIF all over the quantity 1 plus KIV over L. Okay, so for the propane, let's try to solve for the flow rate of propane in the liquid phase. That would be 0.30 multiplied by 1000 all over 1 plus the K of the propane, that is the K of the propane multiplied by V 900 over 100. That will give you now 4.7. The same thing goes for N-butane, N-pentane, and N-hexane. And you now solve for the value of L. Okay, this is now the computed value of L. So checking, the first assumption, L is equal to 100%. The computed L is equal to 149. So L assumption is equal to L computed. Therefore, our conclusion is that we proceed with another assumption or with another trial because L computed and L assumption is not equal. Okay, second assumption, let's say that the L is equal to 488.6. If we know that L is equal to 488.6, what would be the value for V? That would be 511.4. So that's it. So again, we have here the composition of the feed. This is the value of K. Wala namang magbabago dyan. Okay? Because temperature and pressure did not change. That's why K will not change. Again, Li, ano uli si Li? Li represents the flow rate of species I in the liquid phase. Okay, ulitin lang din natin yung ginawa natin kanina. Okay, so ano lang ba magbabago dito? V over L. So itong V over L lang na ito yung magbabago. So we have here the propane, the 36, and butane 28.5, and pentane 81.6, and hexane is 342.5. The summation of all the L here will just be equal to 488.6. So ano yung assumption natin kanina? That L is equal to 488.6. The computed L is equal to 488.6. Therefore, L assumption is equal to L computed. Therefore, we can now proceed with the calculation. So if that is the case, paano natin ngayon makukuha yung composition sa ating liquid phase? So again, alalahanin natin that Zi represents, paulit-ulit ko lang sinasabi, but Zi represents the composition in the feed. Okay? This is the composition in the feed. So if the composition of the feed is multiplied with the flow rate of the feed, what do we have? The flow rate of the species I, or Fi. Okay? So that would be, this is 0.3 multiplied by 1000, that will give you 300. 0.10 multiplied by 1000, that's 100, so on and so forth. Again, okay? So for Li, alam na natin yung Li because kanina, yung L assumed natin and yung L computed natin is the same. So it holds true that this is the value for your Li. Ano yung Li na to? Dito natin yan nakuha. Ito yun. So this is now the flow rate of species in the liquid phase. Now to solve for the percent composition, the fraction composition, the mole fraction of species in the liquid phase, you will have here the flow rate of species over the flow rate of L. Okay, so that would be 36 divided by what is our L? 488.6. For propane, that will give you 0.74. For N-butane, that's 0.058, 0.0167, and 0.701. The summation of this will just be equal to 1.001, which is acceptable, which is very near 1. Okay, so we have now here the value, the composition in the liquid phase. Oops. Now we proceed now with the value of the composition in the vapor phase. So again, what is Fi is equal to ZIF? This will give you the flow rate of the species in the feed. Okay, this is your flow rate of the species in the feed. Li represents the flow rate of species in the liquid phase. Now, if I subtract here Fi, again, what is Fi? The flow rate of the species in the feed minus that of the flow rate in the liquid phase, that will give me now the flow rate of the species in the vapor phase. This is simple material balance, okay? So that would be 300 minus 36 will be equal to 264. The same goes for N-butane, for N-pentane, and for N-hexane, okay? Now, to solve for the composition of the vapor phase, that would be the flow rate of the species all over the V. And that would be 264 over 511.4 for propane will just be equal to 0.516, and the rest follows. So this is now the composition in your vapor phase. This is now the composition in your liquid phase. So that's it. Maybe we can have another exercises for this. I will just post it in Canvas. Okay, so I hope that you learn from this discussion so that you will be able to ace the assessment task ahead of you. Thank you very much.